Hello physics students, we are entering into chapter 3, which is all about vectors. We know a lot about vectors already. We've done some things with them already in the class, but chapter 3 revisits vectors to make sure we have a very solid foundation on vectors before we move into further chapters, because they are so foundational to everything we're going to be doing from here on out. So remember that vectors are contrasted with scalars. Scalars are things that you can fully describe just with one single number. They just have one number, like mass, temperature, volume. Those can just be one single number. But a vector has to have more than just a number to describe it. A lot of times a vector is described with two numbers or more. So a quantity having both a magnitude and a direction. That's what a vector is. The geometric representation of a vector is an arrow with the tail of the arrow. That's this part. That's the tail. That's the head. The tail of the arrow is placed at the point where the measurement is made. So if this is the car or the skateboard or whatever it might be, and it's going 5 meters per second, then you put the tail of the vector on that dot where the skateboard is, and you send the vector with its head at the other end of it to whatever direction it's going. And you try to make the size or length of that vector proportional to the number given here. All right, we label vectors by putting a little arrow above them. Most of the time when I handwrite those things, you handwrite them with a little half an arrow. Just, you'll see as we go. Suppose Sam starts from his front door, takes a walk, and ends up 200 feet to the northeast of where he started. So Sam takes this walk. He kind of meanders a little bit, but he ends up right here. Sam's displacement vector is this blue line right here, simply putting the tail where he started from and the head where he ended up. And this is called Sam's displacement vector, the geometrical representation. All right, an algebraic representation might be of the format like this. It's more than just a 200. You have to say it's 200 feet, but then a further description is to say northeast. Now that's not a very precise way to list a vector, but it's one way to list a vector. We'll talk about more precise ways. The magnitude of Sam's displacement, in other words, the size or the amount of his displacement, is, you can write that as absolute value bars around that vector symbol, or you can just put the S without a vector symbol above it, and that means the magnitude of S, of the vector S, and that is 200 feet, which is the distance between his initial and final points. Sam and Bill are neighbors. They both walk 200 feet to the northeast of their own front doors. Bill's displacement, B, 200 feet northeast, has the same magnitude and direction as Sam's displacement, S. So there's Bill's displacement vector, and it's B. Sam's displacement vector, that's S. Two vectors are equal if they have the same magnitude and direction. So vector B and vector S are equivalent vectors. It doesn't matter that they're in two different places. You can kind of slide these vectors anywhere you want them. You could slide B down here to S, or slide S up there to B, and they would be right on top of one another, as if they were the same vector. And so they are the same equivalent vectors. All right. A hiker's displacement is 4 miles to the east, then 3 miles to the north, as shown. Okay, so the hiker goes 4 miles to the east, then he walks 3 miles to the north. And so vector C is his net displacement. That means his overall displacement. So you just start vector C with its tail where Sam started. Oh, it's not Sam anymore, is it? Where the hiker started. And you put the head of vector C where the hiker ended up. And this is the net displacement vector, the overall displacement vector. All right, you can see that it makes a right triangle. Because A and B are at right angles, the magnitude of C can be given by the Pythagorean theorem. All right, to describe the direction of C, we find this angle right here. You can do that by taking the arctan of 3/4, and you find it to be 37 degrees. So altogether, the hiker's net displacement vector is, if you did the Pythagorean theorem, you'd find it would be 5 miles. And then here's a much better way than just saying northeast, is to write it as an angle. 37 degrees. Notice they say north of east, and it's important to distinguish that between east of north. So 37 degrees north of east would mean it's this angle right here is 37 degrees to the north of straight east. So here's straight east, you go 37 degrees to the north, and that's that angle. All right, that's different than saying 37 degrees east of north. All right, which of the vectors in the second row shows A plus B? If you remember how to add these vectors, we've talked about it before. You add vectors, you can add these vectors more than one way. Here's the way that I normally do it. I take vector A right here. That's vector A. And you put vector B with its tail on A's head. So tail to head. So here's the I'm shifting B and I'm putting its tail starting where the head of A stopped. And there's vector B. And then the overall result of adding A and B would start where A started and end where B ended. So it starts where the first vector started and it ends where the last vector ends. And so this would be the overall result of A plus B. And so that is choice C. Example 3.1. A bird flies 100 miles due east from a tree, then 50 meters northwest. So when it says northwest, it means at a 45-degree angle between north and west. So that is 45 degrees north of west, or you could even say 45 degrees west of north, because they're the same thing in that case, in the special case of 45 degrees. What is the bird's net displacement? Okay, you can see this graphically. All right, I'm going to show you a few different ways to think about this. Here is 100 meters due east right here. And after that, from there, you add the next vector, 50 meters northwest at a 45-degree angle. So that's that right there. And so the overall result would start where the first one started and end where the last one ended. And so this would be the net result. The net resultant vector would be that. That's the net displacement. All right. Now, what about, can we get more precise than just a picture? Of course we can. All right, what this example is about to show is how you can actually use the law of cosines to figure out C here. And certainly you can do it that way. Once they figure out that the length of C is that right there, then they use that to actually find the angle phi using, again, another law of cosines equation. Now, I'm going to show you a much better way, I think, to do it than having to do that. Okay, let me just go ahead and show you. What you do is you break each vector down into its components. All right, half the battle in physics is being able to break things down into their components. So we have I'm breaking both of these vectors. I have one vector, let's just call it vector 1, that is 100 miles just straight up east. So if I break that down into its vertical and horizontal components, that's going to be 100 miles straight up to the east, and it's to the right, so it's positive 100, and 0 miles to the north. And so that's how I express the vector most of the time. I put parentheses around it. I put my horizontal component at the top, my vertical component at the bottom. Okay. Now my next vector, vector 2, is 50 miles northwest. All right. The way that I break that down into components, and it always works, and it's very simple. I always get a standard angle. A standard angle. That means an angle that would be measured from standard position in the coordinate plane. If you need a little reminder of that, the coordinate plane is right here. This positive x-axis is 0. As you go around this way, this is counterclockwise. That's the positive direction. That would be 90. Keep going. That's 180. Keep going. That's 270. Keep going. All the way around will be 360. Okay. So if we're talking about northwest, northwest would be right here. And it would be, so it would be 90 plus what? Plus 45. So that overall, my angle would be 135 degrees if I write it as a standard angle. And if you do that, that's going to make it very easy. So I'm going to say at 135 degrees. So instead of northwest, I'm going to say at 135 degrees. And then the way that I can get it into components is simply by saying it's 50 cosine of 135 for my horizontal component and 50 sine of 135 for my vertical component. And it works every time. If you use the standard angle, it works every time. And what's great about a standard angle is it gets you the correct SIGN sign for the components every time without having to think much about it. There are other ways to do it. You could, think about it like this and have the 50 and have to figure out, use law of cosines, or even kind of say, well, I guess I can do it like this and say that that vertical component is such and such, and this horizontal component is such and such, and that's going to be cosine of 45, and that's going to be sine of 45. But then you have to, if you use the 45-degree angle, you're going to have to manually insert the correct SIGN sign based on the direction, whether it's going left or right or up and down or whatever. The standard angle takes care of the business for you. It takes care of all that sign business for you without any vagueness, without any confusion, without any doubt. It just does it. That's the beautiful thing about a standard angle. So now, to get the result, we just add these two bad boys. The resultant vector, C, is just going to equal 100, 0, plus 50 cosine 135 and 50 sine 135. And you just add them straight across, like the top components will add together, 100 plus 50 cosine 35 to get my overall horizontal component, and 0 plus 50 sine 35 to get my overall vertical component. All right, let me use my calculator real quick to figure out what that is. All right, here's what I get in my calculator. When I add 100 plus 50 cosine 35, I get 64.64. When I add 0 plus 50 sine 35, sine 135, I should say. I forgot to put my 1 right there. You get 35.36. And so those are my components of my resultant vector. So that means that this C vector here has a horizontal component right here of 64.64, and it has a vertical component here of 35.36. Okay, so now one way to express C is simply this. This is called a component vector. Okay, and that's one very legitimate way to express a vector. You might also be asked to express the vector as a magnitude and direction angle. Okay, so let me do it that way. All right, if I express C with a magnitude and a direction angle, all right, here's C. To get its magnitude, I Pythagorize the components. In other words, think of each one of these components as the legs of a right triangle of which you're trying to find the hypotenuse. So you just Pythagorize it by doing the square root of the horizontal component squared plus the vertical component squared. And that gets you your magnitude, your hypotenuse. All right, when I did this in my calculator, I got 73.68 as the magnitude of C. Okay, that is the magnitude of vector C. In other words, that's the magnitude of the displacement of the bird that we're talking about here. What about its direction angle? Direction angle, you might give it as a standard angle, or you might give it as a direction, like a cardinal direction angle in this case. And all of those are legit ways to communicate it. Since this thing is in the first quadrant, the standard angle is going to be the same as the cardinal direction angle. So the way that I would do that, I'm always going to just be thinking about this thing as a right triangle. These are the legs of the right triangle. Here's the vertical leg, 35.36. Here's the horizontal leg, 64.64. And so the vertical leg is always the opposite. The horizontal leg is always the adjacent. And so you're always going to be doing the arctan of the vertical opposite over the adjacent. So the vertical, 35.36, divided by the adjacent, which is the horizontal, 64.64. And that will get you the reference angle for your vector. Now, when we're in the first quadrant, the reference angle is the same thing as the standard angle. So no problem. If we weren't in the first quadrant, we would have to do a little bit more thinking to go from the reference angle to the standard angle. Let me do this on my calculator. Arctan of 35.36 divided by 64.64. I get 28.6, basically 28.7 degrees. So theta equals 28.7 degrees. That's what that angle is right there. So as a standard angle, it's 28.7 degrees. Or if you wanted to give it as a cardinal direction angle, cardinal direction means like north, south, east, west. This would be 28.7 degrees north of east. So here is where the example itself, they list it as a magnitude and a cardinal direction angle. 74 meters, 29 degrees north of east, which they just rounded 28.7 to 29. All right, that was a good example that did a lot for us. All right, you might want to, if you need to go rewind this and go back over that, feel free to, because that was a lot. That was kind of a summary of the whole doggone unit in that example. Parallelogram rule for vector addition. It is often convenient to draw two vectors with their tails together, as shown in figure A below. So you got vector E and vector D happening here. Both of them happen on one point here. So they're happening at the same time on one object, which is why it's convenient in this case to draw them with their tails together. To evaluate the result, which we might call F, which is D plus E, you could move E over and use the tip to tail rule, which I call the tail to head rule, or head to tail. So you're putting the tail of E on the head of D. So here's D, and you're adding E by putting it tail to head, and then the result starts where D started and stops where E stops. And that's the result, F. That's kind of the typical way we do it. That's what I normally do, is I can imagine it that way and do it that way. But there is another way to do it, which is just as good, just as valid, and you might like it better. So we'll explain it here. Alternatively, you can find it as the diagonal of the parallelogram defined by D and E. So here's D and E drawn together. So let me go back to A and kind of do it. Imagine it being done here. You're just kind of making it into a parallelogram. Kind of drawing, just kind of making this into a parallelogram, as these are the kind of the two sides of a parallelogram, two adjacent sides. And so the resultant vector would start at the one corner of the parallelogram where we started and end up in the opposite corner of the parallelogram that we just finished. So that's another good way to do it. And look, you can see that it accomplishes the same thing. And it really is kind of accomplishing the same thing anyway, because drawing this parallelogram is the same thing as moving E over here, right? Or if you draw this part, it's the same thing as moving D up here, tail to head. So hopefully you can see that is very much doing the same thing. Either way you want to think about it, it's totally fine. Vector addition is easily extended to more than two vectors. The hiker The figure shows the path of a hiker moving from initial position 0 to position 1, then 2, 3, and finally 4. So the hiker starts here, and then he takes, first of all, he takes displacement d vector d1 and ends up here. Then he does displacement vector d2 and ends up here. Then he does displacement vector d3 and ends up here. Then he does displacement vector d4 and ends up here. And so the overall displacement, the net displacement vector, would start exactly at the first place he started from and end at exactly the last place he ended up at. And so this is the net displacement vector right here. All right, the four segments are described by those, and you can get that net displacement vector algebraically, not just graphically, but algebraically, by just adding every one of those displacements back to back to back to back. All right. Moving on. More vector mathematics. The length of B is stretched. So if you have this vector A and you multiply vector A by some scalar C, then vector A stretches or shrinks by a factor of C. If C is bigger than 1, it's going to stretch. If C is less than 1, it's going to shrink. And it's going to do it proportional to that C. So if C was a 2, the length of the result would be twice as long as what it started as. If it was a 3, it would be 3 times as long. If it was a 1/3, it would be 1/3 as long. All right. The 0 vector has a length 0 and negative of a vector. All right, here's A. To get negative A, you just flip that thing around so that its tail would start where its head was and its head would end up where its tail was. Multiplication by a negative scalar just flips the thing around and stretches it by whatever factor of that scalar. Subtraction is best thought of, or most simply thought of, as addition of the opposite. So if you wanted to do A minus C, you would do A and then add the opposite of C. So turn C around, put it tail to head, and it would go right here. And so that would be A minus C. And again, we would just start where we started, end up where we finished, and that would be the result. So it's just like addition, but you just, instead of thinking of it as subtraction, think of it as adding the opposite. All right. You can also do the subtraction method using parallelograms as well, but you're doing A and you're doing the opposite of C, and you're making a parallelogram out of that, and starting the resultant vector at the corner of the parallelogram where we started and ending up at the opposite corner of the parallelogram, and that's your resultant vector. That's doing the same thing. You can see that that and that are the same resultant vector. All right, quick check. Which of the vectors in the second row shows 2A minus B? So here's A and here's B. Which one of these choices best represents if you were to do 2A minus B? All right, pause it and think about it. Answer it. All right, 2A. That means I'm going to stretch A by a factor of 2. So I'm going to kind of guesstimate that. Maybe it's right there. And then I'm adding the opposite of B. So the opposite of B would turn B around. And so there's 2A, there's minus B, and so it would start here and end up there. So the choice that looks best like that would be choice A. Coordinate systems and vector components. A coordinate system is an artificially imposed grid that you place on a problem. You are free to choose where to place the origin and how to orient the axes. Below is a conventional XY coordinate system and the 4 quadrants 1 through 4. The figure shows a vector A and an XY coordinate system that we've chosen. We can define 2 new vectors parallel to the axes that we call the component vectors of A, such that A equals the X component of A plus the Y component of A. This is doing exactly what I said earlier. So if you have this vector A, you can break it down into its components. All right, one of its components would be A sub X. The other component would be A sub Y, and they would go directly in the X direction and directly in the Y direction. You could think of it as a parallelogram like that, or you could think of it as a right triangle. Again, it's the same thing. But either way, A sub x would be the horizontal piece. A sub y would be the vertical piece, whether or not you thought about it as being here or being here. All right, so that's A sub x. That's A sub y. All right, we have broken A into two perpendicular vectors that are parallel to the coordinate axes. This is called the decomposition of A into its component vectors. All right, let me just show you how you could do that very easily by using the angle here, whatever that angle might be. It might be theta. And so the components would be, this would be, the horizontal component would be A cosine theta. The vertical component would be A sine theta. That would be an easy way to break it into components. Suppose a vector A has been decomposed into component vectors A sub x and A sub y parallel. We can describe each component vector with a single number called the component. All right? The component tells us how big the component vector is, and with its sign, which ends of the axis the component vector points toward. Shown to the right are two examples of determining the components of a vector. All right, so if you have this vector right here, you break it down into its components, you can see that the horizontal component, just count it. Let's see, you start here at 1, you end up at 4, so that's 1, 2, 3. So the horizontal component is 3. And then look at the vertical component. We start here at 1, we end up here at 3, so that's 1, 2. So the vertical component is 2. So I would write that as that. That would be my component vector. All right. This guy, here's my vector. If I want to break that vector down into components, here is the horizontal component. So I'm going this way, 1, 2, that's -2 in the horizontal. And then I go this way, so I go up 1, 2 in the vertical. So -2, +2 would be the component vector for this guy. All right, hopefully that seemed very simple to you. All right, quick check. What are the x and y components of this vector? All right, go ahead and figure that out for yourself. All right, hopefully you paused it. The x component would be 2. The y component would be 3. All right, so choice B. What about that vector? All right, I can go ahead and tell you the choices right here are wrong. It's just wrong. So go ahead and pause it and see if you can figure it out while knowing these choices are wrong. All right, hopefully you paused it, but we can see here is the horizontal component, that's 3. Here is the vertical component, that's -4. So 3, -4, and you can see that's not even a choice. The thing is going to tell us wrong right here. This is absolutely wrong, just wrong. So shame on you, Pearson, for giving us a wrong slide, but trust me, that is wrong. The answer is 3, -4. Notice they write theirs with like an ordered pair with a comma. That's not usually how I do mine, but it's fine either way. All right, see if you can figure out the components of this vector. All right, pause it. Hopefully you did. And here we go. There is the x component. And since we're going this way, it's going to be -4 if we count that. And the y component would be this. And we're going up +2. So that's -4, 2. Choice D. We will frequently need to decompose a vector into its components. We will also sometimes need to reassemble a vector from its components. So if you have these horizontal and vertical components, you could turn it into, instead of the component vector, you could turn it back into the overall resultant vector with a magnitude and a direction angle, as we show in the earlier example. That earlier example really did everything that I'm teaching for the whole rest of all the slides. The figure to the right shows how to move back and forth between geometric and component representations of a vector. All right, so yeah, so if you want the magnitude, you Pythagorize the components. If you want the angle, you tangerize the components. Yeah, I made those words up. Feel free to use them because those words are awesome. Go forth and spread those words to the rest of the world. If a component vector points left or down, you must manually insert a minus sign in front of the component as done for b sub y in the figure to the right. No, you don't. Not if you use a standard angle, you don't. Now, if you don't use a standard angle, you're going to have to manually insert the correct sign sometimes. But if you use a standard angle, the signs will take care of themselves. So just keep that in mind. Also, if you use a standard angle, the horizontal component will always be found by using cosine of that standard angle, and the vertical component will always be found using sine of that standard angle all the time. But if you don't use the standard angle, like here, they're using an angle here, which is an angle with the vertical instead of with the horizontal. It's an angle with the y-axis instead of the x-axis. Notice they're going to have to use cosine to find the vertical component and use sine to find the horizontal component. I don't like that. Too much room for mistake. Too much thinking I would have to do. All I'm doing, brothers and sisters, is using the standard angle, and it takes care of horizontal and vertical issues, and it takes care of positive and negative issues all at the same time. As you can see, I'm a big proponent of using a standard angle. The role of sines and cosines can be reversed depending if you do it not my way. The angle used to define the direction is almost always between 0 and 90 degrees. Not if you do it my way with a standard angle. So yeah, if I was using this, my standard angle method here, and using this, I would say, okay, I have to go all the way around to here, and that's 270 plus whatever the rest of that is, and that would be my standard angle that I would be using. And that's not hard to do, but once you do that part, everything takes care of itself. All right, example 3.3. Finding the components of an acceleration vector. Seen from above, a hummingbird's acceleration is 6 meters per second squared, 30 degrees south of west. Okay, that's the acceleration vector. It gives me the magnitude, 6, gives me the direction, 30 degrees south of west. Find the x and y components of the acceleration vector A. Now, this will give us a really good chance to use what I'm recommending to you. It's the method I learned at Georgia Tech from a particular professor that I thought that turned out to be really awesome. Let me draw my own. So 30 degrees south of west. Here's my magnitude, and it's 30 degrees south of west. So here's west. So that's south of west by 30 degrees. Now, what is that as a standard angle? Well, it's going to be 180 plus 30, right? Which is just 210. So I'm going to simply break my vector down into components by doing 6 cosine 210 and 6 sine 210. And that's going to do it for me. I could leave it like that, or I could do it in my calculator and get it as a decimal. 6 cosine 210 is negative 5.2, basically. So that's my horizontal component. And do the same thing, but do sine. And my vertical component is negative 3. So that's my answer. Look, they got the same answer, but they had to do a lot more thinking, I think. They put the 30-degree angle here, and then they had to think about what signs go on them, and whether they use cosine for the horizontal and sine for the vertical, or vice versa. And once you use the standard angle, which is easy to figure out usually, you don't have to think about nearly as much after that. Example 3.4. Figure 3.14 shows a car's velocity vector, v. Determine the car's speed and direction of motion. The speed would be the length of this vector. That's the magnitude of the velocity. It's the length of that vector. So what I'm going to do is figure out the components. It's like finding the length of a line segment, right? Kind of like you're using the distance formula or which is based on the Pythagorean theorem. But all I'm doing is figuring out the components, which is going to be -6 and +4, and I'm Pythagorizing that thing. So square root of -6 squared plus 4 squared, which is the square root of 36 plus 16, which is the square root of 52. Is that the square root of 52? If I can add correctly, which I don't always do. I do think I did it right in this case. So you can leave it as a square root of 52, or if you want to get it as a decimal, that's around about 7.2-ish. So my speed is about 7.2 meters per second. And the direction, I'm going to figure out this reference angle right here by tangerizing that thing, or arctangerizing it. The arctan of the vertical over the horizontal. By the way, whenever you arctangerize this thing, don't worry. If something is negative, just put it in there as a positive, because you're finding the reference angle anyway. That's equal to theta reference. So don't put it in as a negative or it might screw you up. So just put it in as a positive. Arctan of 4/6 is 33.69. I'm just going to say 33.7 degrees. And I could express this many ways. I could express it as a standard angle. So I could say theta standard is 180 minus 33.7, which is 146.3 degrees. So I might say that my one way to express it is 7.2 at 146.3 degrees. That's one way to express it. If they want it as a what would I say, as a cardinal direction angle, then you could simply say 7.2 at 33.7 degrees north of west. That's another way to express it. Another way to express it, if you're not even concerned about cardinal directions, if you're more concerned about up, down, left, right, you could say 7.3 at 33.7 degrees up from left. That's another way to express it. There's all kinds of ways, obviously, to express this thing. Let's see what they wanted. Yeah, they just said they used the up from left kind of situation, but they said 34 degrees above the negative x-axis. So that's even another way you could say it. All right, unit vectors. Each vector in the figure to the right has a magnitude of 1, no units, and is parallel to a coordinate axis. A vector with these properties is called a unit vector. These unit vectors have special symbols I and j. So I is the unit vector in the x direction, positive x direction. J is the unit vector in the positive y direction, and they both have a length of 1. Now, why do we care about that? That's another way to express a vector. You can express a vector so many ways. One is the component way, where I'm doing my horizontal component, my vertical component, like that. Another way is with a magnitude and a direction angle. Well, another way is with I and j. So you can express it like this. Let's give an example. So if we got this vector right here, all right, oops. See if you can figure out what it would be, but I'm going to go ahead and tell you. If you want to pause it, pause it. So if we go this way by how much? We went that way, -4. And we go this way by +2. So that's going to be -4i plus 2j. And that is another way to express this thing. And just to show you how this is working, this is -4, and I is the vector 1, 0, plus 2, and j is the vector 0, 1. So that's the vector -4, 0, plus 0, 2, if I multiply those things. And then you add them together, you get the vector -4, 2, which is exactly what I've told you to do before. So they are the exact same thing, just kind of written with a different notation. All right, example 3.5. Run, rabbit, run. A rabbit escaping a fox runs 40 degrees north of west at 10 meters per second. A coordinate system is established with the positive x-axis to the east and the positive y-axis to the north. Write the rabbit's velocity in terms of components and unit vectors. So 10 meters per second at 40 degrees north of west. What do I like to do? I like to get it as a standard angle if I'm breaking it down to components. So I could say that's the same thing as 40 degrees north of west would be, if I put that right here, 40 degrees north of west, that's going to be 40 degrees less than 180 degrees. So that'd be 140 degrees as a standard angle. So break it down to components would be 10 cosine 140, 10 sine 140, which gives me, drop my pen, sorry, which gives me, let me do my calculator here, 10 cosine 140, negative 7.66, and do it with the sine now. 6.43, and there are my components. That's my component vector. All right, negative 7.66 in the x direction, 6.43 in the y direction. If I wanted to also do it with unit vectors, I would simply say that's the same thing as negative 7.66 I plus 6.43 j. So those are both the answers to the question. Notice how they write that. They put it in parentheses and they put the units outside the parentheses. It's kind of like distributing. You distribute it in here. Negative 7.66 I meters per second plus 6.43 j meters per second. All right. So we can perform vector addition by adding the x and y components separately. This method is called algebraic addition. This is what I've been telling you to do the whole time. You break every vector down into its horizontal and vertical components. Then you add the vectors by simply adding their components as if you're combining like terms. Example 3.1 was about a bird that flew 100 miles to the east, then 50 meters to the northwest. Use algebraic addition of vectors to find the bird's net displacement. I'm not going to do that because that's exactly how I showed you to do it the first time. That's how I did it the first time. So, and I think that was a lot easier than having to use law of cosines and such. Okay, I'm on slide 55 now, which talks about tilted axes. When you can tilt your axis instead of, anyway, I'm going to get into that in a different video. So I'm going to end this video here and call it part 1, and we'll keep going with another video in a minute. Good luck with learning this stuff, and let me know if you need any help understanding things, and I hope you can do the problems and are successful on those.